All preamble over, let's get started. So this is the outline of my talk. You can just like quickly skim these. This is basically everything I'm going to talk about. The first is generally an outline about like why we talk about interpretability in the first place. That's like how do we become confident that an AI system is safe, and why I think interpretability is necessary for this, and then what I mean by interpretability. Then the general and ambitious answer to the question I'm talking about in the talk, which is just like what kind of explanations do we want out of like our interpretability methods? What and how much do you need to explain? Current approaches, a taxonomy for different kinds of interpretability methods that we can develop, and high-level interpretability is the thing I work on. So this mild meta note is that I generally speak pretty fast, and I'll be like taking this very fast and loose. So if anyone has any questions or like wants me to repeat anything I said because I said it too fast or you didn't understand it, feel very, very free to interrupt me. Like this is, I generally prefer the style where people interrupt me in the middle of talking to like ask questions. So feel free to do that. Okay. So when we're talking about the safety of an ML system, what do we not know? When we train a competent model, the one thing that we're really certain is that it's going to perform well in the reward signal on the training distribution. This is the one fact that we definitely know while training a competent system. Like there are no further inferences. There are like further inferences we can make, but this is the one thing we know as a concrete fact about the model. We don't know, for instance, like how well did we specify our reward signal such that like our distribution is going to perform well, and so how is the reward signal going to generalize in like new instances, etc. And more generally, what algorithm did our model end up learning on the training distribution such that like when it generalizes our distribution, we can make some assumptions about how it's going to behave. Like there are many reasons why we might be worried about stuff like this, which is, for instance, if you have like a training distribution, you can have a model that pretends to be aligned on the training distribution and then chooses to be deceptive and defects of the distribution and chooses to pursue some reward that it cares about. So like there are many reasons, there's a bunch of failure modes here. That's like an intuition pump of why we care about questions like this in general. Because we really don't have like concrete reason to believe anything more than this first statement about the model that we have, about like how safe it's going to be or what algorithm it's going to learn. So what would help us like answer this question? Well, that's entirely the alignment problem basically. And so one way to simplify this is that we need two things to try and answer this question. First is a high-level understanding of the algorithm that you want the model to learn, such that you're confident that it will be aligned off distribution. This is basically to say that when you're training a model, you need to have some notion of like why you think training this model in particular will lead to good outcomes. So for instance, if you're training like a language model, one conjecture you could make is, okay, this language model is not going to have any goals if it's GPT-4, any long-term coherent goals, multi-episodic, and therefore I think that like when I finish training with this model will be safe for certain. And so like that's one kind of like high-level understanding of the algorithm you want the model to learn. And this is also like pretty hard like when it comes to really complicated models, because you still need to like make conjectures about why you expect that model to be safe in all possible inputs and instances. But like we leave that aside for now. That's one thing we need. The second is how to set up a training process such that we get this algorithm in the end. What I mean by that is, suppose you say, okay, here is like, I trained GPT-6 and the thing I want is just another LLM that just like helps me answer whatever questions I want, and that this algorithm is definitely not going to like defect or become deceptive on like unseen inputs or like doesn't behave in like unpredictable ways. That could be a high level goal, but then how do you structure your training process such that you're really certain that this is the algorithm that the model ends up learning? So we need both of these things to become confident that your AI system is safe. Both something that like tells you, okay, this potential algorithm is safe, and here's the reason why I think you will get this potential algorithm. Now, why are getting these things difficult? In practice, like current models are trained behaviorally, and by that I mean that like when you do apply like RLHF fine-tuning to GPT, basic context here is that RLHF is how you take like a pre-trained model and just like make it into the harmless, helpful assistant that you know. This is done by taking a bunch of outputs that it generates and giving it like ratings, like usually from like 0 to 7 or something, and training it to generate outputs that humans give higher ratings to. Importantly, this just means that you're rating the behavior of the model or its outputs and optimizing it to like increase like what a human would rate its outputs or behavior. And so, as opposed to rating anything about like what its internal cognition is or something to that effect. So, among other things, this implies that our reward signal is underspecified. There are many algorithms that behave identical to each other. For instance, a model that actually cares about what we want and outputs those things is going to behave identical to a model that cares about something else entirely and is choosing to output the things that we want to see on distribution so that we won't like delete it or something. Like those two algorithms are going to behave completely identical on distribution, which is to say that our reward signal does not specify between these two different kinds of algorithms that can be learned. The fully general version of this is there are many, many different kinds of algorithms that you can learn that are going to perform equally well on the training distribution. And it becomes then a question about like inductive biases of neural networks and transformers as to like which one of these you learn, which is like we do not have a good enough theory of deep learning to answer those questions. This is an instance of what I mean by that, which is to say that if you train a neural network on to learn to classify between these two different kinds of objects, which is this blue shape and this red shape, let's say that the thing you want it to learn is to always classify this shape as good and this shape as bad. Empirically speaking, if you train a model to differentiate between these two things and rate this thing as good, the thing it is going to learn is that it should always rate the color red as good. So if it sees a red version of this and a blue version of this, it's always going to rate the red version of this as good. Neural networks, as an empirical fact, almost always pick color over shape. So, but on the training distribution, those two algorithms have like basically equal performance. So you haven't done anything to specify further which algorithm you want. So you wanted the kind of algorithm that liked this shape, but you ended up with the kind of model that just likes the red. So this is an instance of like why behavioral reward training is just like really underspecified in the real world.
I have a question.
Yeah.
You were talking about the signal and being underspecified and the algorithm. Are those interchangeable in some sense, that the signal and the algorithm are actually what the model is using to make it do its decision making, or are they different things?
So yeah, by signal I mean generally like what is incentivized by the loss function. Like basically, signal is more interchangeable with loss function. Like what gradient descent is, what's being used to like guide gradient descent. Yeah, that's a good question. I should definitely be less ambiguous with these terms. Signal generally means like what is the reward we're giving to the model such that like you're training it into certain regions of parameter space. Yeah. So this is to say that like when we're training a model, we have basically no understanding as to like what like internally, what algorithm it's implementing internally. We have little to no mechanistic understanding of our intervention in our models while we're training them. Nothing of our reward signal specifies anything. Nothing of our loss function specifies anything about like what kind of algorithm is implemented internally. None of our loss functions have a term there that says if the model is doing this internally, then do this. Now, there's nothing like that in current training paradigm. We just don't have the technical ability to do that yet. So this brings us to the question of what is interpretability? Like what is the thing that you can try and do that actually does look at something inside a model and tells you and attempt to say something about what kind of algorithm it's learned. So very, very broadly, interpretability is the ability for mechanistic properties or processes of a system to be understood by humans or other observers. There's some reasons for like why this certain phrasings in the sentence are used. Mechanistic properties could be like, is this model implementing some kind of deceptive algorithm, etc. Is this model agentic? Does it have self-awareness? Which are all like properties about the algorithm that's running internally. By humans or other observers is here to disambiguate between like, yeah, it'd be great if humans could understand the algorithm that's running, but it's also sort of fine if you have like a trusted AI observer that's just like monitoring the system and it has understanding of what's happening inside, as long as you trust that AI observer. So the overall definition is meant to be something that translates between what the AI system wants or like what the AI system is doing internally and something in the real world that we can leverage to determine whether or not it's safe. So an ideal version of like this would look like being able to interface with the mechanistic components of a system that inform our oversight. So with RLHF, for instance, the technique that we use to fine-tune our models today, the way that we go about doing it is we oversee the model's outputs and then optimize it to increase whatever rating we would give to those outputs. But so a good version, an ideal version of interpretability would basically look like the ability to look at the things inside a model that we care about and then use that to inform our oversight when we like tell the model that this is a good algorithm to be running or a bad algorithm to be running. The ideal version of this would be the ability to do this completely arbitrarily, to look at some component of the model and say, yep, I like that component and I generally like the algorithm you're running, or I don't like this, you're a deceptive model, you should not have this. So that'd be the ideal version of this. Interpretability is definitely like pre-paradigmatic in that like we are not great at asking the right questions, which I'll get into more later in this talk. As I talk about a bunch of different things in interpretability that people are working on and different ways in which they fail. But yeah, if at any point it seems like I'm not telling you exactly what you should be doing, it's because like, yeah, alignment is pre-paradigmatic and we just have a bunch more problems than we have good answers. Yeah, so there are a bunch of different research agendas we can have that take different angles at tackling different questions, and I'll get into a few of them in a bit. So what is the general answer to the question of what kind of explanations we want? we want a language that lets us robustly map model internals to their equivalent human understandable things in the real world. And what I mean by that is we want something, some tool or method or framework that lets us take different things inside a model and say, yep, this corresponds to this equivalent thing in the world that I understand. So for instance, we can have this algorithm that's like saying, okay, the model cares really, really hard about like this particular component of like the head number, attention head number 3 in layer number 16 or something. And that tells us nothing. But if we can figure out that this specific thing maps onto like that box of paper clips, we can like come up with some understanding as to like what it cares about. In idea, like the ideal version of this is something much more ambitious, which lets us map arbitrary things in the network, like what kind of algorithm it's running in general to just like a human, to the thing in the real world that is that algorithm in human understandable terms, or just like, is this thing deceptive, where deceptive is a concept that exists outside in the real world and not like in the model's own ontology. And I'll get into what I mean by some of those terms in a bit, but yeah. So the reason this is hard is because like if you try to do this naively, like the naive way to go about doing this is to just reverse engineer what every single component of the model is doing. And this is really, really hard because like the things you care about are going to be like arbitrary combinations of a bunch of these different things inside the model. One intuition pump here is that like I sort of understand how atoms work, I sort of understand how transistors work, I sort of understand how like a logic gate works, I sort of understand how Python, the programming language, works, I sort of understand how transformers work. That does not give me an understanding how GPT-4 works internally, even though I understand all of these individual components. Like the intuition pump here is that like understanding these tiny little things inside the network doesn't give you much information as to like macro level explanations of what's happening inside the model, and you run into a bunch of combinatorics problems if you try to just like look at specific things inside the network, try to combine them into the high level expressions you actually do care about. So let's imagine you relax some constraints here. What if you could get away with mapping only to like specific alignment relevant human concepts? Because like one intuition that some people have here is if you try to reverse engineer every single thing inside a model, sure, you're not going to get like a full human level understanding of everything inside the model, but maybe you can get like an understanding of, maybe you can try to like explain everything in full generality anyway. This is really, really hard, but like maybe if you throw enough brute force like research man hours at the problem, you can get you can do that. But like our best interpretability methods, even on like toy models, get you like nowhere near like 90% explainability of something that you're looking at. It gets you like, I'll get into that in a bit, but like some mech-interp results, one example I use here is like copy suppression, which is a mechanistic interpretability result, gets you like 30% explainability of one particular attention head that they were looking at. So they're getting to the point where you can explain like 99.99% of what's happening inside a particular part of the network is itself really, really hard, let alone the problem of like understanding everything about the network to this level of fidelity. So one constraint you could relax here is like, what if you only try to understand specific parts about the network instead of just trying to understand like literally everything inside the network? So this is what like two different, couple of different research areas try to do. These two obvious ones are ELK and high-level interpretability, where ELK is what Zu was talking about earlier. Eliciting latent knowledge, which is the thing that Paul Cristiano came up with. It's a research problem that centers around how to get ML systems to answer questions honestly. And in general, the way this works is try to come up with a way to interface specifically with the notion of truth or latent knowledge within ML systems and try to like extract that robustly. And that requires that you have some kind of way to like information theoretically separate out truth as a notion from everything else within a system. So that's one way to like figure out how to map specifically to one thing inside a system and nothing else. And high-level interpretability, which is what I focus on, tries to do the same thing with objectives, where you try to identify objective structures within networks and try to interpret that to a high level of fidelity. So that's one kind of constraint you can relax. Another one is what if you didn't have to solve for the mapping yourself, but only had to infer certain properties about this. What I mean by this is, what if you didn't have to understand what things in the network map to in the real world, but instead just had to ask some questions about, okay, I don't understand this algorithm, but is this property true of the algorithm that's being run inside the network? One instance of this is what we call mechanistic anomaly detection, which is also something that Paul Cristiano is working on right now, as primarily a solution to ELK, which basically comes about as assume you have a model that is safe to run on the training distribution, for instance. Then off distribution, can you notice the point at which the reasons it's doing something start to change? which is to say that like the model was not being deceptive on the training distribution, it was acting safe, and off distribution it suddenly decides to defect and starts acting deceptive, or like it starts to answer questions for the purpose of like wanting to trick humans or something to that effect. So you yourself don't have the understanding of like, this model, the algorithm the model is implementing is this, and we understand that to a high fidelity. That's why we know that like this isn't safe. Instead, you just have something that looks at the model and says, yep, the mechanism that the model was using, which was safe, is now changed to something else that we no longer know is safe. So that's in one instance of like where you don't understand everything that's happening inside the model, but you can like infer some very specific, useful alignment relevant properties about that mapping from the model internals to the real world. And how to do mechanistic anomaly detection is extremely galaxy brain, so I'm not going to get into that, but it was like, trust Paul Cristiano has some good research intuitions on how to do this.
You have a question?
Yeah.
So, could you explain high-level interpretability?
Yeah, so high-level interpretability is, I do have a section on it later, so I'm just going to cover it briefly now. The general idea is, assume like, take the notion of objectives within systems, where objectives is generally like targets of internal optimization. What those terms mean I can get into, but it generally means like if your model is doing some kind of like runtime inference instead of just having hard-coded heuristics, what does it use to like target that runtime inference? What is it like optimizing for at runtime? And clearly it has something inside its network that tells it here's the thing you care about in the environment. So can you identify that thing and then like interpret robustly what that is? So if you can do that and you expect much of the capabilities of the model to come not from hard-coded heuristics but instead from like runtime reasoning, then you can expect that like the ability to steer that gets you a lot of like leeway over like what the model is going to do. And that's like the thing that you need to understand the most. So like that's basically high-level interpretability. Like the exact research methodology and all of that is a bit involved, but I do get into that later. Does that answer your question? Cool. So here's another constraint you can relax. You imagine you don't need to understand literally everything about the model. You don't need to understand like every attention head, every layer at 99 degree of 50% fidelity. But you do have something that like allows you to look at the model and say, here are the low-level components that I can just like combine up arbitrarily easily to the higher level components I do care about, such that you don't need to solve for like really hard problems around like, the same thing I was talking around earlier about how if you just because you know transistors doesn't mean you can understand GPT-4. What if there was something that conceptually you could just combine together to give you like a rough high-level understanding without having to solve further problems? So SAEs are like sparse autoencoders, which is like something that a lot of mechanistic interpreting people are really excited about nowadays, which is basically the ability to. So the reason SAEs exist is neural networks nowadays, really large ones, generally exhibit like things in superposition, like features, different concepts. They, what's the easiest way to explain this? It's like if you have a really large model and it's trying to learn a really hard task, by default in practice, it's probably going to compress a lot of like different concepts together into like into a smaller number of dimensions than the number of concepts. So if you have like imagine if you have like 2 different neurons, it tries to stuff like 5 different concepts in there by storing them all in like superposition such that in some context, some of these concepts are activated and so on. This makes it much harder to interpret exactly what concept one particular neuron or activation corresponds to. So which is why people are very excited about SAEs, because they're a way to like separate out these concepts from like every single neuron into like something that you can then directly look at. Of course, this is limited by how much you expect that the things you pull out are the right basis to look at, because they still correspond to like low-level circuits within the model that are still like highly descriptive and like that you're trying to infer out like post hoc. So like I generally don't think that these are the right kinds of things to be looking at to like pull out the right kind of like, but to combine together to give you the high-level experiences you care about. And I think empirically this is panned out by how much explanation you're getting out of SAEs. But yeah, that's like one example of like some work toward getting the right kind of principled basis that allows you to like build up to better explanations very, very easily by having like the right ontology to understand the model. Modularity work is also similar to this, that modularity tries to understand what the fundamental unit of computation is in a neural network, basically trying to rediscover what any neural network's ontology is, such that you can just arbitrarily like understand like higher level feature, higher level computations happening inside a network. Yeah, these specific agendas aren't super important. This is just like some intuitions for like how you can make the general problem easier. Yeah, in as much as you don't do this, which is what I say is don't really try to cover the really principal reasons for doing this, you run the problem of robustness, which I'll get into in a bit when I talk about mechanistic interpretability. So, what in our system do we need to explain? there are like specific parts of our system that we really care about explaining. For instance, we don't really care about like, okay, what is our system going to do when it encounters like a series of 3 dogs wearing clown hats? Like, that's not a part of our model's algorithm that we really care about like understanding really well. There are like specific things about our model's algorithm that we care about understanding really well. For instance, whether or not they're deceptive. But we care about that much more than, what is this model going to do in this very particular instance in the real world? Like, if you simply create a brute force understanding of this entire algorithm, you're going to like come across every single piece of explanation that you can come up with as to of the algorithm, and like large parts of that we don't really care. So if you can have some kind of like focused version of this by understanding just the aspects about whether it's deceptive or not, that'd be really, really useful. So it's also like one way to try and like relax the constraints to ask like what kind of things do you need to explain in your system. In general, these end up being really, really hard to like actually interface with. For instance, if you care about deception, how would you go about like actually understanding what part of your system represents deception? Any way you naively go about doing this, if you optimize against it, your deception is going to go to another part of the system. Now, if you try to like search for whether your model is explicitly thinking about deception and you optimize against that, you're probably going to get a model that is deceptive but doesn't explicitly think about using the words deception. It's going to think about like evading human oversight or something. And if you try something even better than that, it just does things that seem competent to it without reasoning about deceiving humans at all. Like, there's many ways to do all of these bad things without like explicitly having to represent them internally in a way that's easily identifiable. The generalizable version of this is the things we care about that would to us make a system safe are not like native properties in the model's ontology. They're like really complex things in our ontology that are onloading onto our understanding of a completely alien system. And so by default, that makes it really hard to like robustly interface with. Like, what is the notion of deception in a fully general sense? What does it mean for a thing to have an objective? What does it mean for a thing to be agentic? Like, these are really hard like conceptual problems to answer, which is what you need to answer if you want to like fully robustly interface with them. And like, you do have to be really, really, really careful with this, because like much of mechanistic interpretability makes the problem of like being really descriptive by looking at a model and saying, okay, clearly this model doesn't have a deception feature anywhere, therefore I'm going to assume it's not deceptive. Yeah. By ontology, I generally mean like the way knowledge and beliefs are represented within a system. So like you and I have like pretty different ontologies, but humans as a class would have like pretty similar ontologies relative to other things. GPT-4 would have its own ontology, which is say like the way it represents information and different things inside it. Yeah.
Is it just like outlook or worldview or something?
Sort of, but it's like it's meant to talk about like the way like different abstractions are ordered around, the way different things are represented, like specific structural claims around like are these things going to be represented like linearly in like some particular way? Does the concept of like happiness and like truth are they close to each other in some space in this ontology? Are they close to each other in that space in the ontology? What is like natively represented here? Like maybe there's some like natural intuition for like how to like better explain an ontology.
I know in philosophy we use ontology to describe the it goes beyond paradigms. It's almost system an umbrella. What umbrella of systems or orientation? Like, for example, the existentialists have an ontology that's very separate from the more logisticians ones.
Yeah, the term is borrowed pretty heavily from philosophy.
Philosophy, right?
Yeah.
Yeah, ontologies, yeah.
Can
So-
you explain the scenario of picking the wrong ontology?
Yeah, so one way to pick the wrong ontology is like a lot of the mechanistic interpretability is quite famous for making like one pretty particular assumption, which is that like they call it the linear representation hypothesis, which is that everything useful about a neural network is going to be represented linearly within the model, such that like if you simply look at like activations, you can then like natively just derive, okay, if the model is going to be deceptive, this is going to be represented linearly. This has a bunch of useful like properties if true, which is that you can leverage a bunch of linear algebra, you can like use something called linear probes to like pull out the things that you care about. So like generally, you'll find a lot of mechanistic interpretive researchers who would say, yep, if a model is deceptive, you can definitely find like a deception feature that's linearly embedded within the network. That's an instance of what I mean by picking the wrong ontology, because like a priori, there is basically no reason for this to be true. And in practice, there are quite a few bits of like evidence as to like things that we care about that aren't linearly represented in the model. Maybe the most famous example is like there was a paper on Othello, this model called Othello GPT, which the original authors said that it does not have a linear world state because like they try to extract whether or not they try to extract the notion of like a player who is having the black pieces and a player who is having the white pieces using a linear probe, and they couldn't, and they required a non-linear probe to do this, which is to say that that concept was not represented linearly within the network. Neil Nanda, who is a mechanistic interpretability alignment researcher, then went in and said, actually, you can do this if instead of looking at black pieces and white pieces, you simply ask, do you have these pieces, or does the opponent have these pieces? And then you can extract that concept using a linear probe. But in practice, like, if you do care about like who has the black pieces and who has the white pieces, you're not going to be able to extract that with using linear probes. So like, there are concepts that are represented within the network in some way that are still not going to be represented linearly. But so like in that sense, the linear representation hypothesis is an instance of you picking the wrong ontology and how to view your model. Does that make sense?
Who are the people are highly influential in this space? You mentioned Neil Nanda.
Yeah. So Neil Nanda is definitely one of them. Actually, let me just check something.
Neil Nanda is N-E-A-L.
Okay, yeah. So
Can you spell that out?
Yeah. Neil.
So the mechanistic interpretability slide is in 2 pages. I'll get to it then. Yeah,
Okay, sure, you get to it.
I go into detail on some of these in a bit.
Thank you, Aaron.
Yeah. Just remind me to do it then.
Thank you.
But yeah, so there's a reason we really need to be careful when you like say you only need to understand specific parts of our systems. By not picking the wrong ontology or not trying to pick an ontology, that means you then need to like solve for a problem of, okay, how do you identify the thing that you want to like explain? So this is like when most of my research which goes into like understanding objectives within systems. To me, the part of the problem that I focus on right now is, okay, how do you robustly extract an objective from any system? Because you can't make any assumptions about being able to go in and say that like, okay, it's going to be represented in one layer, it's going to be like located in like this one particular part of the network. It could be just like sparsely located anywhere in like a really weird representation. So you need to be really careful with that. But that does mean that you have to like solve for a problem of extracting the right thing. But on the upside, that means you don't need to explain everything about the model, because once you've identified this, you can just explain that very particular aspect. The things we care about are highly non-trivial properties of the system. It's hard to translate in all ontologies, is what I was like talking about earlier. But like the things we care about are like complex things that can make sense in our ontology that we're trying to onload onto like completely alien systems, and so like we can't make any assumptions about how they're going to be represented there. Causal scrubbing. This line is like not super important, but like causal scrubbing is this piece of alignment work from this organization called Redwood Research from a couple of years ago, where they basically tried to like come up with. Causal scrubbing is a way to try and benchmark mechanistic interpretability explanations, where causal scrubbing is about the idea that says if you try and come up with a mechanistic interpretability hypothesis as to this part of the model does this thing, what happens when you like use that explanation to just like remove that one particular part of the network? You look at the behavior of the model before and after that, like how much of your explanation about that your mechanistic interpretability hypothesis gives you, how much of that difference in behavior / like things that generally happen are you able to explain? And the results from causal scrubbing are, well, one way to put this is that Redwood Research used to work on interpretability, then they did the causal scrubbing thing, and no one there now works on interpretability, because they all realized, wow, interpretability is really hard. So it's just like, yeah, causal scrubbing is one piece of evidence, because every time they tried running causal scrubbing on basically any mechanistic interpretability algorithm or hypothesis, they found, wow, this just gets terrible performance across the board on basically everything. That you definitely can make progress on this, but that basically convinced everyone at Redwood Research that interpretability is much harder than they thought. And that's why you have to like do other things instead. So this is why I'm more excited about like things like this that focus on very specific parts of the system you can try to explain. But yeah, coming up precise hypothesis in interpretability is just like really hard. And I'll get into it in a bit as like how mistake people commonly make. So one way to go about my interpretability is the alternative to the thing I mentioned in the previous slide, is just to try and explain as much of the system as you can. Like GPT-4 is 1.8 trillion parameters. Can you explain what every single parameter does to a high degree of fidelity? And the question then becomes, how much do we need to explain? Like if we feel like we can explain like 50% of like everything that's happening there, are we going to be satisfied with that? Are we satisfied if we explain 80%? Are we satisfied if we explain 90%? And so on and so on. Like there are different like degrees here in how much like we feel like we need to explain. One intuition pump for why I think it's like this threshold is like really high is that explanations and laws aren't one-to-one. If you come up with like an understanding of your system that captures like 50% of the loss that your model had on training data set, you could be like, okay, my model captures 50%, my explanation captures 50% of everything interesting happening within the network. And then you can be like, this is great, because I've captured at least half of everything interesting in my model, and I haven't found anything damaging yet. One intuition bump for why this statement is true and why you can't like make that kind of reasoning is that if you explain 98% of the loss that GPT-4 has, you basically get a GPT 3.5 level model, because GPT 3.5 has roughly 98% of the loss of GPT-4. So all that interestingness is contained in the last like 1 to 2% there. And if you get to like GPT-5, this difference becomes even more profound, because like increasingly the loss is going to be like log points instead of like linear percentage points. So if you get to like really powerful models, you're going to want like 99.99% explanation of everything that's happening there, as opposed to like 50%, because basically all the interestingness, all the really powerful capabilities are contained in that last like 1 to 2% or like 0.1 to 0.2% or so of the loss that's happening there. So your explanation needs to be that good, and that's like really hard. Current mechanistic interpretability basically looks at what's happening inside a model, looks at certain activations that are happening, looks at like when those neurons get activated. Like one really hacky mech-interp method is you give it a prompt, you just look at what neurons get activated, and then say, okay, this activation corresponds to this input, which is like a really descriptive method, and is extremely noisy in capturing basically anything interesting. One instance is the copy suppression paper, which I referred to earlier, by Callum McDougall, Neil Nanda, and Arthur Conway, where they identify something within GPT-2 that does what they call copy suppression, which is to say that like if you identify 2 copies of something nearby, the model like tries to suppress having a third copy to prevent like arbitrary repetition within models. So they identify this as an attention head, and they say, okay, so this clearly is the attention head corresponding to something we call copy suppression. But when they try to limit this attention head to only doing copy suppression, which by their explanation shouldn't like affect the performance at all, it degrades that attention head's performance to like 30 to 40%. Like that basically says that their explanation has captured 30 to 40% of why that one particular attention head was interesting. And this was like considered a really good paper at the time. It still is a really good paper. It just goes to show like how hard it is to get like anywhere near this degree of like explainability with our mechanistic interpretability algorithms. So I've been saying the word mechanistic interpretability a lot. So what do I mean by mechanistic interpretability? The most trivial definition is just bottom-up reverse engineering. Most mechanistic interpretability defines itself as, can you identify like low-level circuits or low-level concepts within these systems and like understand those really well. And the idea here being that if you can understand those really well, you can build that up to a more holistic understanding of everything that's happening inside the model. And so that's like what a lot of like basically all mainstream mechanistic interpretability is doing this nowadays. Like everyone working at Anthropic is doing this, everyone working at OpenAI is doing this, everyone working at DeepMind is doing this. Basically all the independent interpretability researchers are also doing this, everyone working on interpretability in academia is doing this. There are like, to the best of my understanding, like 5 to 6 people who are working on like something that explicitly is not bottom-up interpretability, but so most mechanistic interpretability is bottom-up reverse engineering of like circuits and features. Like I mentioned before, sparse autoencoders definitely do give you like a more principled basis to operate in terms of like understanding, having like slightly better explanations, slightly better understanding of like these are the concepts we are looking at. So for instance, if you like look at an attention head and separate those into concepts, you can be like, okay, so this concept corresponds to like a giraffe's head or something. And an SAE will definitely give you that concept in isolation, but like you're still using like descriptive ways to understand what that concept is. You're not like deriving from first principles that like this particular neuron corresponds to like giraffe head. You're like looking at inputs and seeing what they trigger on, and then inferring that they're corresponding to these things. So like SAEs still don't solve the fundamental problem, is that you have no way to fully understand exactly what algorithm is being implemented. Yeah, this isn't like super important, but like the right kind of basis would basically allow you to build a more complex dynamics, which is that if you want to do bottom-up reverse engineering of the system, the right way to go about doing it is to start from like the right kind of like fundamental units to build up to. So work on modularity has tried to do this in the past. To the best of my knowledge, the people who have been working on this gave up working on it because they decided that it's too hard. But like if you, in ideality, like this is basically what you should do if you're trying to do like reverse engineering. Try to identify what are the proper fundamental units to identify, what are the actually fundamental circuits in the network, what are the actual fundamental concepts being represented within the network, such that if you identify those, you can just like identify how everything fits together neatly to give you higher level interesting behavior. Like I mentioned before, recovering loss to the degree of precision necessary is really hard this way, and optimistically it gets you like average case solutions to one cluster of problems. And by that I mean mechanistic interpretability's main hope in my eyes is to get you something that, like, if you get GPT-6 and it turns out to be like transformatively powerful, then mechanistic interpretability can definitely like try and look at the model and see whether or not it's like has some deception feature embedded in there, and then don't try to optimize against it, don't try to fine tune it, just say this model is deceptive and throw it away. Like that's definitely one thing you can try to do. That still relies on the assumption that like your deception is going to be represented within that model in a way that your mechanistic interpretability tools can identify. And it doesn't let you like fix the problem, because fixing the problem requires that your tools be much better. It requires that you be able to fix it without like the deception going somewhere else where your tools can't identify. But this is like the main hope for mechanistic interpretability in my eyes. And like to the best of my understanding, people who like really have thought about alignment for a while would agree that like this is the main hope for mechanistic interpretability. Not worst case, but average case solutions to one very particular cluster of problems that revolves around like all of these things being natively represented in ways that like aren't really abstract by default, which is like not a very good hope. But yeah, I can also speak to like some people who are working on interesting mechanistic interpretability approaches, which is like Neil Nanda is definitely like one really good one. He does some really interesting work. He also has like a bunch of really good like resources on getting started on mechanistic interpretability, like a lot of them. Like he's written many things about like getting started on mechanistic interpretability.
Looks like you're gonna dump a lot of like resources. Maybe I can create a thread in design members channel to dump those resources. What's the website for Neil?
Actually, I can just find it honestly.
Yeah. Neilnanda.io.
Yeah, neilnanda.io, and just like he has a tab at the very top that says mechanistic interpretability, and you can like, well, not exactly this. Yeah, concrete steps to get started in transform mechanistic interpretability, concrete mechanistic interpretability explainer and glossary, stuff like that.
And Arun, I know I'm not sure if you covered this, but do you plan to share your slides, or are you open to sharing your slides?
Yeah, I sent it to you on Messenger. Yeah.
Okay, cool. Good to check. I will forward to Saya, folks.
Yeah, there are definitely like the Anthropic interpretability team is probably like the next is probably like the people who are doing the best interpretability research right now, by a good margin, I would say. They're definitely the people who like discovered SAEs, who like discovered superposition and all of these different things. Yeah, so the Anthropic interpretability team, basically all of them, like Callum McDougall, Nelson Elraje, Chris Sola, who basically invented the entire field of mechanistic interpretability, who co-founded Anthropic and is sort of leading the Anthropic interpretability team. Adam German, all of these people are like really good interpretability researchers and like generally good people to look at. But the Anthropic interpretability team, Neil Nanda leads the DeepMind interpretability team. He used to work at the Anthropic interpretability team and then went to found the DeepMind interpretability team. OpenAI also apparently has an interpretability team. I don't know of literally anything they've done that's interesting, but they apparently do have an interpretability team. I don't recommend like going to find what they've done that's super interesting. But yeah, Anthropic and DeepMind definitely have interpretability teams that are pretty good. Yeah, Neil Nanda, Chris Sola are probably the two best names if you're not like looking at all. Chris Sola has a bunch of like foundational work on mechanistic interpretability that are pretty good to look at. But yeah, that's mechanistic interpretability. So, like I said, mechanistic interpretability definitely does not give you like the degree of precision necessary right now, and it's like really hard. But it's definitely the field is growing literally explosively. Like at this point, there are like over 100 people working on mechanistic interpretability alone easily. In the last maths is an alignment research fellowship program. In the last maths cohort, like between 1/2 and 2/3 of the entire cohort worked on some form of mechanistic interpretability, for reference, of all the people working on alignment there. So like it's definitely the kind of thing that if you get like 10,000 to 100,000 people working on mechanistic interpretability, that's a lot of research hours. Like that might be enough to like actually get you the degree of precision you want there. But like in terms of net tractability as opposed to just like how likely do you expect it to be on the counterfactual, mechanistic interpretability is still like really hard. But it's definitely the kind of thing that you absorb a lot of people easily. But like on the margin, if you're like thinking about like if you have no research preferences and you're like what seems like the most impactful thing for you to work on, I'd say that like, yeah, the thing that works if you have 100,000 people working on it is probably not the best thing. Here's another instance of like something else that people are working on called latent adversarial training. I told that you read a paper earlier.
Yeah, the ML safety paper lunch reading group read a paper about the unknown failure modes that that arrive from that could be addressed with latent adversarial training.
Yeah. So look at like one reframe of a problem I mentioned earlier, which is that you really don't know how your model is going to behave off distribution. Imagine if you could like identify all the places in which your model is going to behave badly and then train on those during training. That'd be really good, and that's what usually people do with adversarial training. Like usually in ML, people just like if you want to like cover places, aspects of your distribution that you expect to find but like can't train for directly, you use adversarial training to find those places during training and then train on those. This is really hard because in full generality, because some inputs you are not going to be able to find. The canonical example which comes from Paul Luciano is imagine your model chooses to become deceptive and dangerous only when it sees the factorization of RSA 2048, which requires solving a cryptographically hard problem. In the real world, at some point in the future, maybe that factorization will exist in the real world, but it's not something that like you're going to be able to like identify during adversarial training because it requires you solving a ridiculously hard cryptographic problem. So, doing normal adversarial training, there are definitely like inputs that you're not going to be able to find directly. So you're never going to be able to cover like the full scope of the distribution. So one way to go about maybe one way to go about like solving this problem is to not search for adversarial inputs, but search for adversarial pseudo inputs. By that what I mean is like you have some notion of what it means to be an input of RSA containing RSA 2048. Can you use that to search for what the model would do in that scenario? Like that's a really weird framing, but bear with me for a second, I swear it makes sense. Latent adversarial training is operationalize this as can you come up with some way to edit your model's internals such that it believes it has seen the factorization of RSA 2048, right? It seems pretty straightforward. Like you just edit the model's like early layers to make it believe that it has seen this one very particular input without you having to generate that input yourself. And that way you can like see what the rest of the model's like layers would react to.
Just can you describe a little bit more what the latent space?
Yeah, so the latent space is like so latent space is also like abstracting over something pretty hard here, but like it's generally meant to be in like the space, the dimensional space comprising all possible combinations of inputs and like internal like parameters within the model. Like it's just generally like the internal like parameter space of the model, which is like if you have 1,000 parameter model, it's 1,000 dimensional space, and you basically like edit it in such a way that like it's going to like the parameters are going to like activations are going to behave in very particular ways. So like yeah, just the latent space is basically just like the model's internal like reasoning space sort of.
Kind of scope.
Yeah, sort of, yeah.
Thank you.
And so edit interventions on the latent space basically means like taking one activation and just like making it something else, or like zeroing out the activations in one layer or something. These are all like possible interventions on the latent space. LAT basically looks like doing something in the early layers that like makes it behave as if functionally it just seen this very particular input. In general, like LAT basically looks like trying to come up with like edits on the latent space, as in the early layers, tries to edit the activations in such a way that it maximizes the loss of the network. The intuition here being that like if your model is going to become deceptive, it's going to like then do things that you don't like, and therefore if you have a train signal active right now, that's going to result in really bad loss. So if you then manage to edit your model's internals in some way that like makes it do something bad, and there is a really like the one trigger that says, oh, if I'm going to see this input, then I'm going to do bad things, that would be the easiest trigger to pull. That would be the easiest edit to make. In practice, this doesn't like look quite that simple. There is a problem of just like fucking up everything inside your model. Excuse me if I'm not allowed to swear on campus. There's a problem of messing up everything inside your model and just like having it generate a bunch of random gibberish that also performs really badly against the reward signal. And there's no way to like in full generality separate out like bad and dangerous things from just like random gibberish while making edits on the model's latent space. Like this is really hard. And so one way to go about solving this would be like, again, to operate in the right ontology, just come up with some way to like make interventions such that you're making interventions that preserve the model's like coherence and like capabilities, but still makes it like act dangerously. That requires like solving for what you need for a model to be coherent but still dangerous. Like again, it requires like treating the model in the right ontology, etc., and so on. Any questions on what the next slide?
I'm posting a thread in questions and discussions. So Slack question channel questions discussions. The thread of resources out there. Yeah, just flagging. You had a question.
Yeah, can you like explain exactly how you go about like latent adversarial training? Like how do you come up with like this was these examples for that kind of thing? Or,
These
like,
examples?
Or like how do you find like examples or like kind of adversarial examples which can produce like an deceptive algorithm like this?
Yeah, so there is like, this is basically like the, where is the loss function? I forget where it is exactly, but like, this is sort of what you do here, which is that when you assume that like when you get some input in the environment, the model's internal activations look like S of X. Like its activations are set to like this particular value and its output is Y of S, right? So the adversary, what it does here is takes these things and tries to modify the latents such that the output then does really, really badly on the loss function. So it's basically like a trivial optimization problem at that point.
Sure. So then I guess the fundamental assumption then would be that like performing really, really badly like on the loss function that was used to train the model originally, I assume. Right?
Yeah, it still requires that like your loss function would perform badly on like outputs you consider dangerous, yeah.
Okay, yeah.
Yeah, so like if your output is still the kind that like, you know, still looks good to your water rating model, this would definitely not capture that. But like one reason for why that might not be a huge deal is that like you can still try to like elicit like what your model's behavior would be like long in the future and then like have your loss function operate on that. But yeah, there are definitely like failure modes that this does not cover. This covers like, can you cover the cases where like your model behaves in obviously bad ways of distribution?
Okay, sure.
Yeah.
In the paper, I noticed it said surgeon, and the metaphor I was thinking of originally was it seems like brain surgery on a neural network. Is that the metaphor that you?
Yeah, basically, yeah. I mean, you are literally like trying to like snip at things in the brain of the model. So yeah, surgeon is like, it's ironic because like this post came out in like mid 2022, and when it came out, it had like 20 upvotes on Less Wrong, and I remember like being weirded out when it came out because like, wow, this seems like one of the most promising alignment research ideas I've heard in a long time, and it's sitting at like 20 upvotes. I made a post all the way back then as to like, wow, this post is cool. And no one was working on it for so long. And now there are like 5 different groups of people working on it together after 2 years, but yeah.
I was looking into the paper earlier today about LAC that said they're working with latent representations as opposed to the input space, and I just wanted to understand the main difference between the two.
Yeah, so the latent space generally refers to like the space of like what value the activations are set to, and the input space is like the space of all possible like inputs. Like in one way to think about it is that space of all possible inputs is much larger. Like if you have like a language model, the space of all possible inputs is basically like space of anything that could happen in the real world. Whereas the space of activations is like a fixed thing that corresponds to like the number of like activations, the number of parameters that the model has, and number of dimensions that the model has. So it's a much smaller space to operate in. So if you're making edits in that space, it basically says you're editing like specific activations of the model to be like different values. Which is an easier problem because then you don't run into like RSA 2048 style factorization problems because the space is much smaller. Questions? Alright, cool. Here's another instance of like another thing that people have worked on, which is CCS, which stands for Contrast Consistent Search, by Colin Burns, who currently works in the superalignment team at OpenAI. Now this is an interesting one because at the time it came out, many people thought this was extremely interesting. Many people still think it's extremely interesting. The idea is, well, this is the broad idea. You come up with some property that you think is like necessary for all kinds of truth representations within neural networks, and then you try to extract all structures that have this property. This is pretty similar to eliciting latent knowledge that we talked about earlier, where this tries to conjecture that like, yeah, if you try to like extract every property, every system that has, every structure that has this one property, this works for systems. That was meant to be, it doesn't work. It doesn't work. The property it specifically tries to use is, can you train can you like pass in two sentences to a model, two prompts to a model. One like, is this the sky is blue and the sky is green, and see what the activations are in each case, and then train a probe such that you're extracting some structure that is set to one in one case and 0 in the other case, basically differentiating between what the model considers to be true and false in both cases, and some other constraints as well. And you basically conjecture that this is enough to capture like truth representation within the model. If you're like familiar with computer science at all, theoretical computer science, you'll understand like why this is really not capturing the thing you care about. You're not measuring what you care about, what you think you're measuring then, because the thing that you're actually capturing there is something loosely correlated, a really weak proxy for the thing you care about. And in practice, like people have tried to replicate this paper and no one succeeded. Like it's still an interesting method. I do think it gets you some amount of leeway in like controlling the model, but no one has succeeded in replicating this paper. The DeepMind alignment team has tried, multiple other people have independently tried, and no one has succeeded in replicating this paper. And independently of that, people have tried using the method in a bunch of other contexts, and it's also still not worked then. CCS is basically the kind of thing that worked for one model and one data set and had some really good results then. And this is the kind of problem you run into when you do really descriptive things on neural networks, which is that you run into kinds of things that like overfit specifically on the kinds of things you have and make no further like predictions or hypotheses about like how things are supposed to work in general. It doesn't replicate very well, it doesn't generalize to other contexts. If it sounds like I'm bragging on it a lot, it's because people still really love this without realizing the paper has never once replicated. It definitely has the right spirit though. The thing you should be trying to do is trying to identify like, properties about like things you care about, like truth representations, and try to extract them robustly. The problem that CCS did was they found one property. They found the property that like, you know, the activations have to be set to 1 for true statements and 0 for false statements that you think that, and then they tried to like go really hard on like extracting structures that have that one property, instead of just like iterating quicker and understanding like here are more properties that like flesh out the operationalization of truth representations even more. Like that's the right way to go about doing this. There are like so many properties that you can think of that may exist for truth representations within systems. And if you have like a dozen of those, maybe that gets you some amount of robustness. But going really hard on one property is just really not going to work. Unlearning is another class of like machine learning approaches, which is basically about like how can you make your system unlearn some concept. Latent adversarial training was sort of related to this. Stephen Casper, who currently leads most efforts on latent adversarial training, he started out doing unlearning stuff, sort of. Unlearning is basically like, can you take a model and make it forget all information related to like creating bioweapons or something? There are obvious reasons why this might be useful. This is also really hard because when you say, can you make your formal model forget everything related to making bioweapons, what you mean by information related to bioweapons is a specific arbitrary boundary you're drawing around like knowledge space, and it's really hard to again translate that into a completely different ontology. In practice, when you try to do unlearning, it never ends up being robust. State of the art here is like a Microsoft research paper from a couple of months ago that tried to erase the knowledge of Harry Potter from a model, which should be relatively straightforward. And they did in fact claim that they got some pretty good results. But then you interact with the model and just start the story with a young boy with black hair and a scar on his forehead, and continues like talking about Harry Potter without ever using the words Harry Potter. So like the conceptual boundary you want to draw there around the information present is like pretty arbitrary and pretty complex, such that like any metric you're going to use to like penalize certain structures within the network are always going to like, are very rarely going to capture the full complexity of the things you care about. This again comes back to you care about very complex things that make sense in your ontology, and you're unable to like translate them into another ontology robustly, and you're always going to like capture some properties of that thing but never the full thing. Quite easy to record information related to prompt interact with, the Harry Potter thing. Rome is one instance of unlearning where like someone tried to set up a model's internal such that like it always localizes information in one particular part of the network, and then they try to like edit the model such that like it believes the Eiffel Tower is in Rome and not Paris, hence why the method is called Rome, rank 1 model editing. And it claimed to have like really good performance here, because once you do this, every time you ask the model like the Eiffel Tower is in, it'll say Rome, and similar things like that. But like over all possible prompts you try this on, it only works like 40% of the time. Even when you explicitly try to construct your model such that like you preserve some kind of locality of the things you care about, you get 40%. And as you can remember, 40% is not nearly as good as it sounds when you think about like you needing like 99% instead of like a linear representation of like we're 40% of the way. So like yeah, most methods that try to do things like this are not very good because they make very strong assumptions about like how much you understand about the model in a structural perspective.
Aaron just time check. It's 8:15. I know you have like six more slides. So, but just a heads up for time check. Yeah.
Yeah, cool. So yeah, that's basically like a summary of like a bunch of different things that people are trying in interpretability. Now I'm going to like quickly just dive into like different ways to differentiate interpretability methods. This is borrowed pretty heavily from Evan Hubinger's Interpretability Tech Tree, which is a post he wrote on Les Wang a while ago. If you have gone, or if you understand that. I am changing some of the terms here because I think that some of the terms that he uses in that post are pretty ambiguous and like not very well specified, which is the reason I have a slide here at all. So low-level interpretability is the ability to robustly understand individual local components in the model. This is basically what mechanistic interpretability tries to be right now. In Evan's post, he calls this best case interpretability. And high-level interpretability is the ability to robustly interface with a component that may be present anywhere in the system. By which I mean, like, if your model has a deceptive circuit somewhere, or like deceptive reasoning happening anywhere in your system, you have to be able to search over your entire system to be able to identify that. Or if there's some knowledge that present somewhere that you want to identify, or like truth representations corresponding to some question you're asking it, you want to be able to search over the system everywhere to be able to robustly interface with that one particular aspect. So what I call high-level interpretability. Evan calls it worst-case interpretability. And the reason I think these terms are ambiguous is because there is another distinction you could make, which is average case interpretability versus worst case interpretability. But average case interpretability is the kind of method you can use to look at a system and say, okay, this system is being deceptive because I can see the things in here that are very suspicious. But if you try to optimize against those tools, all guarantees are off, and your model can immediately start like looking very, very safe by your tools while still being deceptive in like arbitrary ways. Whereas worst case interpretability tools are the kind that allows you to train against them, and if they start to look safe, that means they actually are safe. So worst case interpretability tools are obviously much, much, much harder. They're also much, much more powerful. Because in the first case, that basically means you spend $100 billion training GPT-7 and you use your interpretability tools on it, find out that it's deceptively aligned, and you're left with three choices. One, deploy the model anyway. Two, train against your interpretability tools and then try to hope that like it doesn't end up being deceptive anyway, because their average case interpretability tools are probably not going to work. And in the third case, throw your $100 billion model away. And none of those three options are really very good. So you're probably going to need like worst case interpretability tools in practice. Evan Hubinger's main theory of change relies on using average case interpretability tools to identify whether GPT-7 is deceptive or not, and if it is deceptive, use that to convince everyone to shut down together. That is his primary theory of change. Evan Hubinger is more pessimistic than I am about like how you solve alignment, but even so, that doesn't seem like a very good theory of change. So yeah, high-level interpretability is the thing I'm working on. I'm not going to like, go too much into detail about this. In fact, this will probably be my last slide. Yeah, so high-level interpretability is basically the idea of identify a robust and generalizable specification of high-level properties in the real world relevant to safety and target at high-level structural analogs in the neural net. What I mean by that is take the notion of objectives. Now, by objectives, I mean targets of internal search or optimization or runtime reasoning, etc. And this is definitely a human understanding. This is definitely a concept that makes sense in a human sense. Like optimization is a thing that exists in the real world, but like it's a boundary we're drawing around a concept that makes sense to us. So you can't make any assumptions about how search or optimization will be represented within the neural network, let alone like what the target of that search or optimization is going to be, which is what I mean by objectives. So if you want to identify it, that means you have to try to come up with an ontology-independent representation or specification of objectives and such. And that means you have to come up with like some very, very general understanding of what an objective is in any system, and then apply the specification to your system and be like, yep, this is this thing's objective. You could like make several conjectures here. CCS, which we talked about earlier, is one instance of something that tries to do this for truth representations, where you try to say, here is one property that is true of like truth representations in systems, and try to extract that. In practice, when you try to actually do this, that looks like coming up with many, many properties that in combination describes a fully general and robust specification. So most of my work goes into constructing this specification, basically coming up with more properties that like separate out objective structures from other structures within a system. And the better you get at this, one of the nice points of this is that the more you do this, the more control you get over your network. The next few slides here, which I'm not going to go into in too much detail, are basically talking about here is like one property that I try to use to extract objectives from a network, and that gives you some really good predictive power over like where in your model you find certain things, like where in your model do you find like internal representations of like where the model is then going to go in a maze environment and such. So like it definitely doesn't like beat state of the art in terms of controlling the model, but it definitely does give you like a very, very non-trivial amount of predictive power as to where your model is going to go to in a maze. So in this instance, it's like if you look at like, if you expect like these are different layers in a model, and then you say, okay, if your model ends up like having the cheese location, if you expect there are two different things in a maze, a cheese and a red gem, and you find that like cheese is highly represented according to this probe in the later layers, you can say that this model is maybe going to the cheese. And you find that empirically this does hold up. The model does in fact go toward the cheese when it's trained to like when the model is like the kind that always goes toward the cheese. And if it's the kind of model that goes toward the red gem, you'll find that those things are flipped. So this gives you some predictive power over the model, and like even better versions of this will get you like much greater like control over what the model is doing, what its objective is, and so on and so on. But like yeah, this is basically what high-level interpretability is trying to come up with properties that necessarily and sufficiently describe objective properties in a system, and then looking at those structures and trying to like retarget them toward other things, or like understanding what they are, and yeah, something to that effect. And that's high level interpretability and my research agenda. And yeah, probably gonna end my talk there.
Yep. Thank you, Arun. Let's give a round of applause. Yeah. Thank you. That was definitely there's a pretty dense presentation. I will distribute the boba. Q&A can commence. Yeah. So yeah.
I'm sure there are a lot of questions.
Yeah. So many questions.
Yeah.
Is there a paper on that?
Which high-level interpretability? No, there is a less wrong post. I considered converting it into a paper, and I
It's okay,
decided
as long
against
as
it because I'm
it's-
lazy. I think my co-author, Paul Colonesi, is converting this into a paper right now. So there may be a paper on this in a couple of months, but like right now, this is a post
No,
because
that's pretty
writing a
good
post
stuff.
is much easier. So
Yeah.
yeah, it is.
Yeah.
This is not the best. Like this is mainly about like one specific experiment that we ran, which is what the other slides were talking about, the predictive power thing, which I think is pretty interesting. But like yeah, the best resource on high-level interpretability right now is probably this doc, which I can also send to Zoo. This is basically a thing I wrote a few months ago on my overall threat model and theory of change, which like talks a lot about like my motivation for working on high-level interpretability and what I mean by high-level interpretability. All of this stuff basically, different ways in which you can use it. I can send that to Zoo. Yeah. Zoo, I'm sending you a link. Send it in the Slack.
Got it. Okay. Yep.
Oh, thank you.
Okay, yeah. That's probably like the best thing to read about high-level interpretability. Yeah. Hopefully we'll have a paper on this sometime. But yeah, it's definitely not high on my priority list. And even if you have a paper, like it wouldn't contain much of like the conceptual like motivation behind why I work on this. It'll mostly be about specific experiments. But yeah.
I'll pick one for you, Aaron.
Yeah.
Which one would you like to enter the?
Oh man, they did label it. Milk face.
Well, this one's that.
Oh yeah, sunset thing. Oh yeah, I think this is guava. Sunset.
What's the other one?
This is something milk based.
I don't know. I've had like 2 bobas in my life. Give me whichever.
Oh man.
Anybody have a subjective judgment which one's better?
I can't figure it out. I think it's creamy jasmine.
Okay.
Yeah. Sorry, this shouldn't take up discussion time, but Japanese rice tea?
I think guava's less risky for like.
Well, that's risky. Okay, cool.
Right.
Yeah.
The experimental one.
Yeah.
So any more questions?
When you say structural analogs, is there like, you mean like internal geometry being developed by those?
Yeah. So 2 separate questions. I'll answer both of them separately because like yeah, I do not in fact mean that. What I mean is like if we identify like some general specification of objectives, importantly, you're not making structural claims about how you expect it to look, right? But the thing you want to interface with is the structural representation within the network. So you come with some general ontology independent specification of an objective, and then when you identify that thing within the network, you're going to identify its structural representation. That's what I mean by interfacing with its structural analog. But yeah, I do expect like separately to be some kind of like internal geometry here model. There's this one particular alignment research called developmental interpretability that revolves a large part around like how you expect like the internals of models to change over time during training. It revolves in large part around this thing called singular learning theory, which is like a sort of a science of deep learning, but also just a fully general mathematical framework for a bunch of different things. And yeah, that also might be interesting, but yeah, it's a large tangent.
So, rumor has it that, that McInterp should not take up that much space in research. What do you think? Like you did mention, for example, MATS, which is one of the premier programs for alignment research. 1/3 of people are all about McInterp. Is that a problem, Arun?
I swear I didn't plan to. I swear.
What's your balance measure take? Yeah.
So I stand very strongly behind this statement, right? Optimistic, the realistic versions of mechanistic interpretability that you'll get in like the next 5 years or so will get you this average case solutions to one cluster of problems. And I don't know about you, but I'm not very happy if 2/3 of the entire field is focused on average case solutions to one kind of problem. Like there are many other problems, and we really, really want worst case solutions to a bunch of them. So like it's definitely the kind of thing I'm glad like if a bunch of people work on, but it's like it solves like such a small part of the problem in realistic trajectories. So like yeah, I'd be happy if like 1/5 of the field worked in it, or maybe even 1/3, just because the kind of thing they could benefit from a lot of manpower. But if there is some way to trade off between people working on mechanistic interpretability and people working on other things, I would much rather than work on like other things in the margin. There are like so many people working on mechanistic interpretability right now. My guess is that like in 6 months there are going to be more people working on mechanistic interpretability than there are the entire rest of alignment combined, and that's like not a very good number. And like yeah, so like, but it is the kind of thing that like definitely is so very, very, very easy for like and tractable for people to get into. So like maybe you aren't exactly trading off against other things, but it does like contribute to field epistemics, and like I think in general the prevalence of McInterp has led to people reasoning about things in a lot worse way than they would, etc. But yeah, go ahead, your question.
Oh.
Yeah.
Oh yeah, sorry. When you speak about average pace, are you talking about complexity? Is it like time complexity or other?
No, I mean like it's like inspired by that, but the idea here is like by average case you mean like something that works if you don't optimize against it, and like something that works in like so the reason it's inspired by the complexity class thing is that if you in the time complexity case you describe average case and worst case as being like the median cluster of like how long you expect it to take, and the worst case is being like the literal like furthest you can get out of it. And the analog here is that average case is basically like in the median case, before you apply any optimization pressure, can you capture like an explanation of your model that's meaningful? And the worst case means that like if you throw as much optimization as possible to break your interpretability tools, throw as much power as you can to like make your tools fail and just completely break down, does it still work? And so like that's the reason it like holds up. Like average case is basically meant to say that like before, when you just have your model fresh out of training, does your interpretability tool work? And then when you start like train against your interpretability tool, does it work? Those are like two different things. So like yeah, that's what the average case just means like does it work before you apply an optimization problem.
And is high level interpretability working with the worst case solution?
Optimistically, yeah. I mean,
okay.
Getting to a worst case solution is really, really, really hard. Gradient descent is extremely popular in optimizing and breaking your tools, and it's really, really hard to specify what you want. But yeah, if you come up with a robust metric for objectives, then you shouldn't expect it to break. I think in practice, you're going to get like, optimistically, you're going to get like a decently robust metric, and then you're going to have to hope that like you don't apply enough optimization power to break it before like we get transformative AI systems that can like fill in the rest of the research for us or something. Like if we can get to 2035, if we can survive until 2035 with like the level of robustness of our solution without actively optimizing against it or something, the real world also throws optimization power against you. That's one of the reasons you'd want it, even if you didn't like actively optimize against it. If you can get it like 2035, if you can get a couple of years with like transformatively powerful systems, and you can accelerate like AI alignment and interpretability research like 1,000-fold in a year, and you have a robust enough solutions to get that much time at the end, then you can get the AI system to solve the rest of the problem for you. But like that's like maybe one big hope you can have.
I share your doc in the questions discussion Slack channel thread, which should be public to everyone, including non-members. Yeah.
Could you give an explanation for why CCS wasn't a very effective method? I think you talked about it briefly. But
Yeah, so there are two large reasons. The first, which I expected to happen the day I saw the paper in the first place, was like, this seems like a method that is like trying to hinge on a very specific property about truth representations, right? Which, like, that property alone, you shouldn't expect to like fully be enough to describe all kinds of ways in which truth representations can be represented. So like the first thing is that like in a bunch of other contexts for a bunch of other models, it doesn't really generalize very well. Like you don't really capture like if you use CCS, you don't get to like actually get at the truth representations within your models. The other thing is that the paper just doesn't replicate. Like who was it?
Colin Burns. Oh, sorry.
Yeah, but like I'm trying to find the DeepMind alignments team, like their attempt at replicating this. Yeah, this paper basically. You can see here like CCS seems exciting to us and we are keen to apply it, and they now think that it's unlikely to be directly helpful for implementation of alignment strategies, etc., etc. And there's like let me see. There's like so many posts about like CCS that they basically talk about like how it really doesn't work. Yeah, there we go. What discovering knowledge, latent knowledge did and did not find. And basically like a bunch of comments talk about like there's a specific post that talks about CCS just being not very good because of like
so the intuition though in general is that like it's very difficult to like define truth representations across like a variety of models.
yeah, and yeah, the generalized version here is like eliciting latent knowledge. This is the thing that I described Paul Krishnan working on. This is like the full general problem of eliciting latent knowledge. So also like all the problems that he describes that you can come up with when you try to do this. There are like many more problems as well, but this is like a 106-page attempt at trying to describe in the first place. CCS was basically Colin Burns' attempt at like, what if you don't need to worry about all of these problems, and what if you can just like empirically get better results anyway? And turns out that you really can't, or maybe you can, but you definitely need something much stronger than CCS. But yeah, this is basically a 106 version of 106-page like treatise as to like how hard it is to identify truth abstractions, yeah. Which I also recommend. You have the link to this,
Yep, sending it. Yeah.
Any other questions?
What are your thoughts on like the current state of unlearning methods? And do you think it's like
Current state of what?
unlearning methods? I imagine that there are probably a variety of approaches to that specific type of problem. And do you think it's like kind of promising, I suppose?
I think that like, well, Stephen Casper is the person who like I've spoken to the most who works on unlearning, and I remember that like when I was telling him, also okay, so here's why I don't think unlearning will actually work for like worst case alignment guarantees. He's like, yeah, I agree, but also the thing I really care about is preventing like misuse from AI systems as opposed to like takeover risk. He is still worried about takeover risk, but he also cares like a lot about misuse risk. So like if you care about that kind of stuff, then like the unlearning stuff we have is pretty great. Like if you can just get like something that sort of works without a lot of optimization pressure applied against it, then like that's enough to prevent a lot of misuse risk. So if that's your main concern, then yes. I definitely am not excited about like most unlearning approaches for like getting you anywhere near to worst case guarantees. I think that getting to worst case guarantees is like requires solving like some fundamental problems that like we really haven't solved yet. Something to do with ontology translation, translating the concept you care about from your ontology to the models. Latent adversarial training is maybe the most optimistic of all of them. It's also very new, but even then I don't expect it to get very far without solving that fundamental problem.
If there are no more questions, we can break to socials. Like literally just.
I have one more crazy question for you. It's probably impossible to answer, but I just wanted to see what your thought is.
I love impossible questions. Here.
Okay, so Joshua Bengio the other day was doing an interview with Brian Greene, and at the very end he started talking about his alignment research, and he mentioned that he believes that consciousness is mathematically mappable, and that he thinks it's a key to interpretability. And I wanted to see that's what they're working on at University of Toronto. So I wanted to see what your thought about that is. Have you heard about it? Is it crazy, or is it?
So I have 3 different thoughts. 4. The first is I actually attended a talk by Joshua Bengio last week at the place in Berkeley, and to the best of my understanding, the work he is currently doing and his primary alignment research agenda does not depend on solving consciousness. I think I was already not very optimistic about it. If it turns out that is in fact necessary, I would have very surprised opinions about Joshua Bengio's research tastes. Second is, I'm pretty sure, this is a minor note, but I'm pretty sure he was talking about leaving academia to found his own lab to do this because he doesn't trust academia to be fast enough to solve alignment. So like, I don't think University of Toronto is affiliated with this. The third is that like, yeah, I do think consciousness is probably mathematically mappable in a very trivial sense, in that like, it's also a human concept that exists in the real world. And so like, if it's a human concept that actually does exist, then you should be able to come up with some way to like translate it across ontologies anyway, as you can with all human concepts. So like, if that's true, then you should be able to translate the concept of consciousness across ontologies, and so by definition it has to be mathematically mappable. So like, that's different from like the literal notion of consciousness being mathematically mappable, but I expect that if it's a thing that exists, then yeah, that's going to be true. The fourth is that no, I don't think that's going to be necessary for interpretability. Okay. Except in as much as like the ability to translate concepts from one ontology to another is intrinsically necessary for interpretability. Like in that sense, sure, I don't think that's like necessary for like not fully general versions of interpretability to be right. But like yeah, the fully general versions of interpretability also solve that problem. I don't think that is necessary for interpretability though.
Yeah, the part that appealed to me about it was the ability to abstract. Like some of the methods that you discussed, it's like abstraction is really hard.
Yeah.
And bottoms up is even harder.
Yeah.
So, having that somewhere, having it have some kind of understanding of what it's doing, or consciousness of what it's doing, might actually be a key.
Yeah, I agree. In that note, you might be interested in like this one very particular alignment researcher called John Wentworth, and his research agenda called natural abstractions. Like when I described at the very start of this talk, like that the fully general answer to what we want is
which of his John Wentworth's?
probably just like the plan 2023 version. So like when I describe this, he is basically the only person I know of who explicitly tries to get this thing, which is extremely ridiculously ambitious. Like I think I'm ambitious, but I don't think that you need to be this ambitious to solve alignment. But this man is definitely trying to do something this ambitious, like trying to come up with like a fully general notion of how abstractions work in the real world, and have a framework to speak about like everything that we care about in model internals, and everything we care about as human concepts, and everything we care about agency and intelligence and etc. So like he's definitely trying to do that, which is like ambitious as fuck. But like yes, he's trying to do this. So like you might be interested in a few.
What would that even look like? What would that even look like?
Good question. I don't know. I mean, like the prosaic version of like how to describe his plan is that he's trying to come up with a way to like understand like how information is represented within like systems trained inside one kind of environment, and how like information is naturally represented within that environment, and try to build up like those from both ends until they meet at the center, and that would give you an ability to arbitrarily translate between abstractions or information representation within agents and their equivalent things in the environment. So like that's basically like a fully general theory of abstractions. The thing he's working on right now is like what are the most natural ways to represent information within an environment. So things about like information compression and transmitting information at distance, etc., is like sort of what he's working on. The thing he's working on right now is called natural latents, which is like what are the most like within a given system with like certain variables, what are like the latent variables that are learned by that system, like natural to compress things, etc., etc.
Okay. So once you have like an understanding of like how this system like kind of compresses information or uses information, it's unclear to me then how do you like translate that into like, well, how how does that go into like some kind of like translation into like human understandable versions of that information?
Understanding in what?
Like how does that like lead to like
Oh
how
yeah,
do you
yeah. I
translate
mean,
that information to something human
yeah, I mean the
understandable?
intuition here is that like because you're translating between things in the system and things in the real world, the things in the real world are implicitly things that you understand. Like the information that are present in the environment is like the notion of a tree is an abstraction that's natural to the environment, right? So if you can get that, if you can like, figure out like way to translate abstractions into those terms, then you can be like, yep, those are definitely natural abstractions in the real world that I understand. So if you just like, in some sense, like you're translating like abstractions in any kind of system into abstractions in the in the one kind of system who shares a similar ontology to yours, and who implicitly you understand like information representation within. So it's one way to think about is translating information from one kind of ontology to specifically your ontology, or generally like things in the real world.
Okay. Yeah. Then I guess like immediate other questions would just be like, what would like the nature of this translation look like? Are there, I guess this also assumes like, is there like a finite number of these types of like, you know, like abstractions or like these ideas there? Like how do you like robustly like extract this, I suppose? Like, I suppose it also goes to the question of like, what are the types of answers that you want from interpretability too? I suppose like, do you just want like a list of like the model is like, oh, I like cats more than dogs or something like this, or like.
So yeah, it
what
depends
does
on
that
your
mean?
Go ahead. Okay, it depends on your operationalization of abstraction. John Wentworth would say that like, so your model is going to represent like certain latent variables as being like the things it cares about. One way to think about this is like, well, one pretty neat way to think about this is this like recent result around like, this is a result from a couple of weeks ago from a couple of people I know, which basically says that like transformers, if they're like trained to model a hidden Markov model at 3 different states, the residual stream will look like this theoretical prediction of a fractal, right? And there's this particular reason for this, which is that like results from computational mechanics around like how if you have a hidden Markov system with like 3 different variables, predicting that system requires implicitly modeling the system out perfectly and also modeling additional information on top around like how to sync the model to the state it's currently in, and so on and so on, and thus you end up with this fractal. So one reason why John Wentworth found this really interesting is, can you work backward from that? If given this fractal structure, if you identify this as being everything about the model, that clearly means that if you're given this structure, there are 3 latent variables that your model is representing. Can you then back out what those 3 latent variables are? And there's like a fully general version of this, which is that your model has latent variables there. Can you figure out something to go inside the model and identify what those latent variables are? What the most fundamental abstractions your model are using are? So like that's one way of like intuiting it basically. Any other questions?
We can organically wind down, but it is socially acceptable to
Yeah, one of my
read,
competitive advantages is that I have infinite energy to talk about alignment, so feel free to come up to me and ask me questions about alignment at any point.
This is pretty true. At Ivor, Aaron was up talking about around the fire pit till 3 a.m. So yeah.
At EAG, at the last EAG I went to, I didn't sleep.
The EA Global Conference where lots of ASAP people gathered.